Alright, hey everyone, welcome back to another OSCP journey video. Today we're going to take a look again at the last few stack challenges from exploit education or exploit exercises. So we're going to start with stack 4. We did 0 through 3 last time. We're going to try to do 4 through 7 today. I've never actually done 7. I've only done up to 6. I'm not even sure I'm great at doing up to 6. So we may not get all the way there. That's the goal. But for all I know, we'll only get done with 4 and 5. But we'll start and see where we end up. So here is stack 4. This is going to be pretty much the same type of video as the last video. So we're just going to start here and get moving. So when we did stack 3, we looked at environment variables and we overwrote a function pointer. Actually, I don't see where we did environment variables. Stack 3 looks at environment variables, how they can be set, and overriding functions. Not really do anything with actual environment variables like we did in 2. But here we are dealing with environment variable, or we're not dealing with environment variables, sorry, we're dealing with function pointers, and we're redirecting code execution of a function pointer. Stack 4 is going to be similar. We have this when function that we need to get to, that we need to change our code flow to, but we don't have any function pointer to build off of. Instead, we're going off of the primary instruction pointer, or EIP in this case. So yeah, same standard buffer overflow, same buffer, same get vulnerable gets function, and same target, but just a different kind of way to get there through EIP instead of through the function pointer. All right, so let's dive right in. So first, we're gonna SSH into the box, give ourselves a nice bash prompt. All right, now we're gonna run Protostar bin stack 4, and if we type in a bunch of gibberish, nothing happens. If we type in a whole bunch of A's though, you get segmentation fault. So this one really doesn't tell us a whole lot and kind of forces our hand at jumping into GDB, but that's fine. We're no stranger to GDB. Let's jump right in. All right, so we'll GDB stack 4. And here I'm actually going to write some hooks. I got these hooks from Live Overflow. I may modify them a little bit. I don't remember everything off the top of my head. But we're going to take a look at what's on the stack, and we're going to take a look at what's at our current instruction pointer. Because remember, our goal is to override the instruction pointer. Before we get into that, let's break main. Let's set our disassembly flavor to Intel. And let's go ahead and disassemble main. Okay, and we'll disassemble that when function too, so we know we're trying to get to here. This is ultimately the target address that we want to exploit, but we don't have a lot of feedback. Even though we know the exploit's the same, we could probably reuse exploit code from last time. First off, I've restarted the VM since last time, so none of it's saved, and we got to start over, so that's fun. Second off, it's just good practice to keep trying on it. All right, so now we're going to define our hook here before we start stepping into the program. What this is going to do is basically every time we do step in the program, it's going to display some stuff for us that's just kind of helpful. So we're going to find hook stop. So that's what we'll call it. I'm going to be following Live Overflow's formula here, where we're going to print out a piece of the instruction pointer, kind of examine that, and then also examine a chunk of the stack. So EIP is our instruction pointer, ESP is our stack pointer. I believe, let me get this right for myself. So 8WX, I believe this is words. I'm just not sure what exactly all the measurements are. I'd like to actually understand. So WX. Okay, so we're going to display 8 half words, so 32-bit values, and we're going to display them in hexadecimal. So that's what this one is saying. And then 1I, we're going to display one instruction. So we're going to display the instruction and 8 half words of the stack. or sorry, not half words, 8 words of the stack, not half words. I've been saying half words the whole time. I've been reading that wrong. W is words. That's a no-brainer. Yeah, so that's what's gonna go on here. And to end the hook, we'll just type end, and now we can start stepping through our program. So let's run it. Broke. All right, so now we can already kind of see our hook working. Our current instruction is push EBP, so this is what the stack pointer is looking at. This is what is currently on the stack, and we'll kind of see that as we're going through execution. This is just going to really help us debug, especially once we get to that section where we need to overflow. So we're at the gets call now. I'm going to start writing my standard alphabet string to it. E, F, G, H, I. Alright, and then I'm going to copy this for later use. So we'll enter that. And it looks like here we've already written some values on the stack. So there's our hex 4 1s, 4 2s, 4 3s, 4 4. So that's A, B, C, D, E. And as we step through, we'll get to see what happens. So once we get to once we get to return, which this is the end, we're basically at the end of the program now. If we disassemble main, this program is very short. We do a push, move, and sub, load f div address, move, call, gets, and then we leave. As you can remember, this is really it. We're just setting a buffer, calling gets, and that's our main. And then we're trying to redirect to the when function with sprints, but that's it. If we don't get there, then we just leave and return. So our goal here is once we get to this return instruction, we want EIP to return whatever's on top of the stack. In this case, it's a bunch of 5 4s. So if we go back, open a new tab, and go into Python and say hex 5 4, it's our T's. So we're back at our T's again. So if we keep going, we'll see that it can't access the memory address at 535357, which if we kind of take a look at the stack now, which I believe it'd be examine, kind of making stuff up as I go along. Yes, examine string. So this is what's on the stack at the moment. Yeah. So that we've kind of completed everything. So it tried to return to that address and couldn't, which tells me that right before this, that error is a little bit weird because I feel like it would have been the hex 5 4s, but we'll run it again and see what happens. So that's going to be part of playing with this. So we'll run it again, and we'll kind of step through here till we get to that gets call. We'll paste in our stuff, and we'll delete up to the S's because then I'm expecting to have zeros on the stack, right? And that is exactly what happens, I believe. Got 0 0 0 1. That's not exactly what I was looking for. Let's run that again. Get rid of all these up to the S's. So we say 8. ESP. I'm losing my mind. Hold on. Examine. Yeah, okay, so that's kind of what we're looking at. We know that we filled up with our the hex 53 is kind of throwing me off, but I believe I was right. I believe the 5 4s where the T's are is actually correct. So our goal now is we need to write an exploit that will jump to the when function, and we actually want to go ahead and get our when address there before we quit out. So we'll quit. Yep. All right, so now let's go ahead and make an exploit. So we'll call this exploit4.py buffer, and we'll backspace this into the S, and our target address is going to be struct.pack something, and then we'll print buffer plus target address, and we need to remember to import structure. That won't work. All right, so we'll grab the start of when, pop that in as our target address, run python exploit4.py. Looks great. And now we'll come back into GDB. We'll break at main again. We will now define our hook once more. So we'll say examine one instruction at $EIP, and we'll examine words and hex at $ESP, and then we'll feed this our exp4. Keep stepping through. Eventually we get to the gets call. Alright, looks like we've got some values on the stack. Cannot access memory address at 5353. So we have 5353535B. If we just examine ESP, I don't know, examine 100 ESP. EIP maybe? Alright, well, let's just take a look at whatever the heck X53 is. See if we're doing this right. S. Maybe. Alright, that gives us a little bit of an idea. Let's do this. Exploit4. So we've got 3 S's in there. Maybe this is where we need to stop. So this is where we just kind of have to play around with the buffer and see what's going on. We didn't keep going. It looks like we're actually in the when function. Code flow successfully changed. No, we actually... I think we actually did it. Hold on. Hold on now. Let's get this exploit back moving. I think we spoke too soon. I think we weren't moving fast. We weren't moving all the way through the program. We were getting ahead of ourselves. So let's run. All right, so program's terminated now for sure. Let's run this again. keep on stepping through. Eventually we'll get to a return call. It says we can't access the memory address, but our program's not quitting out yet. And now we're in the when function. So it looks like everything worked out exactly as we had intended it. Yeah, it looks like our instruction did indeed get pushed into the right spot. Let's go cat exploit4.py real quick. So see if we can see where this was at. Yeah, here it is, right here. I just missed it because I was too busy paying attention to this that I didn't see right when we were returning the first address on the stack was indeed our target address. Sweet. So we have successfully redirected code execution, which means if we quit this and run stack4 by piping in our exploit4, code flow successfully changed. So sweet, we have successfully solved stack 4. All right, so stack 5 gets interesting because now it's time to introduce shellcode. This is a plain buffer overflow. There's nothing crazy going on here. It's simply a buffer called by gets, and we have to introduce some shellcode into it. So we'll actually write a full payload on this one. Based on that, then if we run stack 5 and we type in some stuff, we get nothing. If we type in a whole bunch of A's, we'll get a seg fault, but that's, I didn't even type in enough A's. We should get a seg fault, but yeah. There's nothing really going on here to give us any feedback. This is pure, we got to get a shell. So when it comes to generating shellcode, there's a lot of things we can do. So I'm going to go to MSF Venom, and I'm going to generate some basic shellcode. I may attempt to, I don't know if I want to attempt to do a reverse shell or not. I think I may want to keep it simple. So what we can do for our shellcode is say MSF Venom list payloads, and we can grep out for Linux. MSF Venom is just a great tool built into the Metasploit framework that generates payloads for you, and you can generate interpreter-based payloads or shell payloads. We've seen this in my tutorial series before, but when it comes to exploit development is really where this shines. You can obviously just generate straight binaries and stuff to drop on boxes, but when you need shellcode for an exploit, we've actually demonstrated this several times. There's an automation tool that I show off with the MS17010 and then the MS08067 exploit. We generate our shellcode from here. So this is just so you don't have to reinvent the wheel. We can get shellcode from here. We can also pull shellcode off the internet. I haven't really decided what I want to do in this case. Let's see what we have available to us and then go from there. Part of me wants to be real cool and do a reverse shell. Just because I can. Yeah, let's just do a... Here's the thing about doing a reverse shell, though. If we do a reverse shell this way, we're not going to get a root shell back, which is part of the cool part of this was getting root. But, hell, we'll do it this way. I want that. I want to show off how you would actually get a shell if this was running as a service, not necessarily root privs. The root privs concept would be the same. You just, instead of doing a reverse shell back, you'd get some standard shellcode that would just spawn bin bash right where you are. You could actually do that with exec here. You could just say, hey, exec bin bash or whatever. Or you could even just have a payload that adds a user that is root, or run chmod or whatever. Like the possibilities are endless here. You just kind of do whatever it is that you are trying to do, but we're going to do a basic 32-bit shell. Let's get our IP address, and what are we over here? IP address. We're on the 2 subnet, so we need our 2 subnet IP address over 2186 as per usual. So MSF Venom, that's P L host equals 192.168.2.186. L port is 1337. do format raw because we just want pure shellcode, and we want our variable to be shellcode. I think. No, hold on. I did that wrong. Format Python. So this will give us a Python-friendly version of the shellcode. So as long as I didn't screw up anything, we'll have this shellcode to work with. It looks like we're good. This is nice and small. Alright, so we can copy this right into our payload, but there's going to be some other stuff we're going to do, but we'll start here. So vim, first off, copy exploit for and exploit 5.py, vim exploit 5.py, and we will copy in our shellcode. And we'll stick our shellcode here, but there's actually more that we're going to want to do. We're going to want to introduce what's called a knop sled. So when it comes to successfully and accurately accessing your shellcode, sometimes putting your shellcode right where you want to execute stuff isn't going to be effective unless you can get it just right. However, what you can do to play off that is introduce what are called knops, which knops are represented by a hex 90. And it just means no operation. So I like to usually fill in like 100 knops or something like that. And what this allows us to do is we put our buffer overflow in, we put in a target address that we want to attempt to jump to somewhere on the stack. And the idea is that we filled up the stack so much with knops, at the end of those knops is the shellcode. So we can point at any one of these addresses that our knops are at, and it creates a knop sled. It just goes, hey, you've overflowed here, and you told me from this point go to this address. Well, at this address, you could put your shellcode, or you could try to line it up. That may not work, but what you could do is just put in a whole bunch of no operations, hit that address, it just sees a bunch of hex 90s, and it says, oh, no op. I'm just going to keep going to no ops until I hit code that can execute. And the code that's going to be at the end of that sled, so to speak, is our shellcode. So it's just going to kind of slide on down into the shellcode, and it's a super handy technique that gives us some wiggle room for where we need to actually put our stuff. So I'm actually going to leave off the shellcode for now when I generate this payload to see how my knops fill up the stack, and see if I actually have a good buffer overflow still, because I may need to adjust things. In fact, I'm going to play around in GDB first. So GDB stack 5, break it main, and we'll write our hook real quick. So hook stop. We'll examine one instruction at EIP, and we'll examine 8 words at ESP, and run this. Eventually we'll get to that gets call. Let's not break ourselves here. Let's copy what we got, fill out the rest. Alright, and let's see what we've got on the stack after we do that. It's a bunch of 5-4s again, so that's our T, so we should be able to kind of reproduce that. But what we really need to look at here, well, actually, nothing yet. There's not a whole lot for us to look at just yet, but what we can do is say run this with exploit 5. Now, as we step through, we will have a whole bunch of knops on the stack to examine once we get to that point. Okay, so we get to this return, and normally we'd want to access this address, right? This would be our target address. This address doesn't exist. So if you remember from our previous exploit, that's why this is here. It's not going to be able to find that. That's not a real spot in memory, or it shouldn't be anyway. Yeah. So it's going to kind of freak out a little bit as it tries to go through. But if we examine just a whole chunk of the stack, the stack pointer, we'll see starting here, we've got our hex 90. So we could pick any one of these addresses or anywhere in between for where our target address needs to be. And then we can see our shellcode will be starting here, right after our knop. So we put in our knops and we can pick one of these addresses and actually put in our shellcode. So let's do that. Let's just pick nice middle of the road address here. And that will be our target address. That's where we want the stack to return to. So hopefully this is all making sense now if this is new to some of you guys. What's going on is that we don't really have anywhere to go, but we can fill up the stack with as much crap as we want. And the stack has addresses. And so once we filled up our all of our crap on the stack, and if part of that crap pile is just some code that we can execute, we can just say, hey, thanks for the address, go run our stuff. That return instruction will pop that address off the stack and say, okay, I'll go run here. It'll see the hex 90s and slide down. So now we're actually going to generate our payload with our shellcode. And that, in theory, should work really well. Now, obviously, we're going to step through this. There we go. Okay. So that took a while. Eventually, it did get there. We need a way to listen to the shell, or listen for the shell. So I'm actually going to minimize this window for now. Start up a new one. We'll start up a netcat listener on port, what was it, 1337. And we'll run this again, exp5. And we'll step through this until we eventually get to... Alright, so we made the call. We see here that the target address, EC, is being pointed to. Keep stepping through. It's doing our NOPs. And eventually we'll slide down and should get a shell. So we're successful so far. There's a lot of NOPs. I could probably just hit continue. But I'll kind of want to see where it'll pop off because I'm not sure. So I'm just going to keep stepping until we get to the end here. I feel confident though because we are indeed in the knop sled. I just don't know where the hell we are. Okay, we're getting somewhere. Looks like we're probably in our shellcode now. I'm just going to hit continue. Oh, okay, sweet, it worked. Alright, so now we got a reverse shell. But, like I said, we're not root. So now, in theory, if we start this up, quit that, this is where I've had trouble before getting this to work, but I think it should. Yep, perfect. That's how you write a full payload. I am so happy that worked. Every other time I've tried it, it hasn't worked, and I'm got a root shell. That is so cool. Okay, so the reason I've only gotten user shells before is because when you run the binary in GDB, it's not running it the same way. So now I've just ran it with set UID permissions actually to have a root shell. That makes this even more awesome. And as you'll notice, in the past I've used MSF Venom in tandem with Mesploit's multi-handler. You can still do that. that's perfectly valid. The multi-handler will also catch regular shells. The only reason I didn't do that this time is because I had just normal shellcode. That's all it is at the end of the day. That's something I've tried to express in my other videos, is all that you're doing with that shell is you can pick a staged or stageless payload, and by doing a staged payload, you can have smaller shellcode that your multi-handler can help you out with, and you can help manage multiple shells, and that's valid to use on the OSCP because all it's doing is exactly what NCAT's doing. It's just easier. It's better management. It's just a good tool. You're using it as a tool. And so that's all we've done here is use MSF Venom to generate shellcode. That's no different than if we were to pull other shellcode off the internet. It just makes things a little bit easier because it's a centralized location. Now, in this case, because it is just shellcode, nothing fancy, we're using a stageless payload, and it's just complete raw shellcode. We're able to get a shell back, and that is awesome. So now we've got a remote root shell. That is so cool. I'm so happy about that. I'm excited. All right, so we've got stacks 6 and 7 next. I think I'm going to save those for another video, partially because I need a bit of a refresher on ret to libc. I've got some notes on it, which is super helpful, but I need to make sure I've got my understanding grounded first before I sit here and bash my head for another hour. This video is already half an hour long. And then stack 7 is looking like some more different stuff I've never done. So we'll introduce this in another video. I feel like this is some major progress right here, though. Whenever you're able to pop a root shell, man, it feels good. So we'll leave it at that while we're on a high note, and we'll jump to stack 6 and 7 in the next video, and then hopefully after that some Windows stuff, and by that time I'll be off to the races with the OSCP. So hope you guys benefited from this video. I hope this is something I'll be able to go back and watch in the future and say, great job, look at myself, you did good things, or at least look at myself and say, wow, I've learned a lot. So I don't know how I'll look at myself in the future, but right now I'm feeling pretty good. With that, drop a like and subscribe if you're enjoying everything. Thanks for watching.